You're not going ahead and build a big airplane. You first build a model and test it in the wind tunnel. Because airplanes are so big, you want to test it on a smaller scale. Well, in the world of materials, and this is called quantum simulators, we want new materials and you have an idea. But if everything is tiny, microscopic, in a real solid material, things are very complicated. So maybe you want to test drive it on an enlarged scale where everything is controlled. And this is the reason motivates the research we do in ultra-cold atoms. Today I focused on our studies of superfluidity, on the work which led to the Nobel Prize, but I already gave you a taste that we studied how electrons can pair. Currently my research is mainly focused on magnetic materials, but this would be the topic for another lecture. And I really glad that I had an opportunity to talk to you, and thank you for your attention.
So the question is there a point of learning about the microscopic structure of Bose Einstein condensate in terms of how the individual atoms behave within the Bose Einstein condensate? Is there a point of developing techniques to learn about the individual atoms, how they behave? Or can we learn something from that about more fundamental things like is it possible to learn something about quantum mechanics by actually tracking or finding how the atoms individually behave inside the Bose Einstein condensate? Am I clear?
Okay. So the question is, in other words, what can we learn by studying atoms in the Bose Einstein condensate? Do we learn something new about quantum mechanics? The big question, or the simple answer is yes. We are studying those quantum mechanical systems to learn more about quantum mechanics. But I should say we are not learning much more about the Schrödinger equation or the simple equation, what a simple particle does quantum mechanics. The research topic is here to find out what happens when many particles act together. So the research to which we are contributing and the understanding which we are advancing is many particle quantum physics. Or to say it even clearer, we are not looking at the Schrödinger equation for single particle. The Schrödinger equation for many particles cannot be exactly solved. So people have to use approximations. They are trying to find better and better solutions. And our research helps to verify solutions or shows where current methods are not adequate. The other question I want to address is when you said, what happens to a single atom in a Bose Einstein condensate? Well, the answer is nothing really happens, because we work in a dilute gas, and each atom is marching in lockstep with the other atom, but each atom is still isolated. And this is actually, so the atom is like an isolated atom, is like a sodium or lithium atom which has been studied in hotter gases. The property of the atom does not change as a function of temperature. But this is actually good, because the atom still has its atomic properties. We can use our laser beams, our radio waves, we can use the power of atomic manipulation, atomic spectroscopy to diagnose the gas. Actually, the fact that the atom behaves like an atom, even in that situation, this is part of the potential which this research has, because the building blocks are well understood. The only thing which we have to learn is what are they doing all together.
Other question?
So you talked earlier in the lecture we had in the class about how the laser cooling actually you can get colder with a larger mass. Does your evaporation process also depend on mass? Can you get colder with the larger mass atoms, or does the evaporation process take it down to the same temperature regardless of what the mass is, and the laser actually depends on how cold you can get it?
Okay, the question is how do the cooling methods depend on the mass of the atoms? I mentioned it in passing. We can use lithium atoms, sodium atoms, rubidium atoms, and rubidium is 12 times heavier than lithium. How does that affect the Bose Einstein condensate if we have something much heavier? And what I taught in class today, in the quantum mechanics class, is that the laser cooling part goes to lower temperature when the mass is heavier. Then we say this is not immediately an advantage, because for Bose Einstein condensation, the heavier the mass, the lower is the temperature you need. So it's not necessarily that the heavier mass, and that's also in practice, it doesn't help you. You have to reach lower temperatures with a heavier mass. You ask about evaporative cooling. The limit of evaporative cooling does not directly depend on mass, it depends on other atomic properties. So therefore, I'm not even able to give you a generic answer. It really depends on which atom you pick and on the specific properties. But the fact is, when it comes to Bose Einstein condensation, we have cooling methods which work pretty much equally well for lighter and heavier atoms. And there is research done on heavier atoms and on lighter atoms. The cooling methods both work. When something works, you don't care if it could possibly work a little bit better. It works well enough to do the research. And now what is important is that the different atoms have different properties. And it's like in biology, you want to look at different animals, at different species. And so we want to look now at Bose Einstein condensates, which consist of different atoms.
So one example of eddy currents that I remember is if you take a copper tube and then you were to drop a magnet down it, it would be slowed down. What would happen if this tube were, say, made out of a superconductor?
Sorry, there was some echo. The question is about a copper tube dropped.
If you take a magnet and drop it in a copper tube, the falling rate would be slowed down because of all the eddy currents. I'm just wondering what would happen if the tube were made by a superconductor. Or what would happen to the magnet?
Okay, so the question is the following. If you take a magnet and drop it through a copper tube, the magnet will not fall as fast as it would in gravity because eddy currents in the copper slow down the magnet. Well, what would happen in a superconductor? The magnet would be levitated, it would stop. Because you create eddy currents, what happens is in a normal copper tube, the magnet falls slower and slower, but now when it falls sufficiently slow, there's enough time for the eddy currents to decay, and eventually you have an equilibrium between the decaying eddy currents and the slow speed of fall. But if the eddy currents would never decay like in a superconductor, you would really stop the motion. Probably the magnet would be reflected, would bounce up and down, reflected by the magnetic field created by the eddy currents. It would be spectacular.
In a brief way, who are a couple of most inspirational physicists that you've heard about, read about, done research on, and stuff?
Who is the most inspirational physicist? I mean, I would immediately point out my postdoctoral mentor. It was my third postdoc position. I came to MIT, and this person was Professor Dave Pritchard. He was so sharp, he was so fast, he was so responsive. I was already a mature scientist in my early 30s, and I suddenly met a person who showed me there is still room to go. And I was working hard to catch up with him, and eventually I did. But it was important for me to find somebody who was challenging me. Maybe you were expecting that I would say Einstein or somebody, but I feel much more inspired by living scientists, which are role models for you. From people whose work I've read, I really love the writings of Richard Feynman. When I was an undergraduate student, the Feynman lectures of physics really changed the way how I thought about physics. And I still occasionally look up something in the Feynman lectures to sort of read it again and remember what he said.
So you showed a graph, and it was just the temperature when they became superconductors.
Yes.
And I noticed that the higher temperature ones are much more complex molecules.
Yes.
Do we know why they're able to be superconductors at such a higher temperature?
Let me just go back to the graph you've mentioned. So we talked about I lost my cursor. Oh, here it is. Okay. That's what happens if you use Okay, so I mentioned that there is a quest for superconducting materials which are superconducting at higher temperature, and you noticed correctly that the materials which have the highest temperature are much more complicated than some of the simple metals which have lower temperature. Well, that's just what it means is the following. In the simple metals, the pairing between the electrons, and this is at the heart of superconductivity, is mediated by phonons. And this is a weak coupling, and therefore the transition temperature is low. In the other materials, the current understanding is that it is some direct interaction of the electrons with each other, in essence, a modified form of the Coulomb interaction, which is much, much stronger. But this is a much more complicated mechanism, and it only happens in more complicated materials. So to some extent, that sort of is an indication that this kind of superconductivity we understand. But if you want to go higher in superconductivity, you have to understand much more complicated physics. And this is what motivates us. We want to, a big goal of my research is to simulate high temperature superconductors using cold atoms.
So then for the future, are you guys looking for much more complicated compounds then compared to like what we see there?
Well, definitely not me. I'm an atomic physicist and I work with ultra-dilute gases. But what we are trying to do is we want to, using our lasers, our radio waves, kind of all the tools of atomic physics, we want to replicate in a simple gas what may be the pairing mechanisms for those complicated materials. So in other words, I will